Hi folks, let's see, the other day we were doing some lead compensation and I sort of ran out of time, and so I just wanted to finish that example off, maybe start it from the beginning just to introduce it and then dig into it a little bit so that you have this workflow down. So here is the plant that we're working with. 2.5 over SS plus 2.5, and steady state error requirement less than or equal to 0.005. So we're going to put that right at 0.005, and that means that we just need to set KC, the let me go down to here, the gain of the compensator equal to 200. And we can get that through a velocity error constant calculation like so. So I'm going to assume that you know how to do that. If you have any questions, let me know. So we now have the gain of the compensator sorted out. So I'm going to put that into the plant and start the analysis from that point. Now if I go to MATLAB and let's have a look at this. Hopefully you have these functions put together, a handful of anonymous functions in a nice tidy little file. Now it's even a little tidier, and I named that file myfunds.m. If you don't have this, you could pause the video now and get these things in. But basically, it's just calculating the fee of the compensator. I'm sorry, calculating the alpha of the compensator based on the fee that we want. How much phase margin do we want from the compensator? So you put that argument in here, and you get out an alpha. And then here's the magnitude drop. So this is how much we have to compensate the magnitude plot by based on our value of alpha. And so on. Let's see, a magnitude and a phase angle of a transfer function using the evalfr command. So make sure you have those handy. They can be pretty useful for playing around with Bode plots. Okay, so let's get the transfer function in there. We've got a loop gain of 2.5 times 200, and the denominator is 2.50. Great. Beautiful looking thing. We're going to start this design by using the margin command. And here is the Bode plot. And we can see that we have a phase margin of 6.4 degrees. Now, I'm going to keep track of that phase margin value, so I'll create a little variable in MATLAB just so I can refer back to it because I'll likely forget. So I'm going to keep track of this frequency 22.3, which is their gain crossover frequency right here. Oops, not right there. Right here. There it is. And, 22.3 thereabouts. We can see the magnitude is about 0. We go down here, and this is our phase margin. So it says negative 174. If you add 180 to that, you'll get the 6.4 degrees of phase margin. So let me get these things in. I'm going to say PM0 for maybe PM original is 6.4. And omega m0 is equal to 22.3. So now I've got those tracked. And what we need, so, we need to have a phase margin of 55 degrees. And if I were so basic to think that I can stick that phase bubble right here and everything will just work fine. Of course, it doesn't work, but we'll try it. And then I would say I just need 55, which is how much phase margin we need for the whole system. Subtract 6.4 from it and get 48.6. So I'll call this phase margin compensator 1 or something and say that that's equal to 48.6. Now I'm going to start using my functions. I better run that little file. This little doofus here, so I'll say run. I had a path there. Sorry about that. So let's see if we got that sorted out. If I do a who's right here, I can see all these wonderful little function handles. And now let's go ahead and calculate alpha, which is equal to this PANG PMC1, 48.6. And I get this. There's my alpha. Pretty exciting. So that is, half of the design. And now I just have to figure out what capital T should be. And if I go back to the slides, I just have to figure out what this capital T is, and we have some, design formulas for that. Where are they? see up here, that are based on this Bode plot of a phase lead compensator. So what I'm going to do is I'm going to pick omega m, that's where I want the phase bubble to be that original gain crossover frequency that of 22.3 that we know is kind of bogus, but let's just see where that gets us. It's kind of saying I'm going to try to put the phase bubble right at 22.3 and, you know, hope for the best. And we'll dig into that, you know, along the way. So I'm going to go T is equal to 1 over, do I have my omega m? I think I do. And I called it omega m0, divided by the square root of alpha. All right, so just as a double check, we go to here and we see, okay, 1 over omega n square root of alpha. Beautiful. So I'll go like that, and now we'll form the compensator. So D1, remember I have the Kc already built into the loop transfer function, so I'm not going to fiddle with that. I'm just going to say that this is equal to a transfer function that looks like so. And there we go. Now, what I'm going to do is I'm going to get, maybe I'll make a new plot. I'll call it figure 2, and I'll just use the Bode command. And I'm going to plot a few things. We're going to plot the original loop transfer function, and now let's plot the loop transfer function and our new compensator. And let's just plot the compensator all by itself, too. So this will plot all 3 of these things on a single set of axes. Oh, what the heck did I do with a margin? Oh my gosh, I meant to say grid. There we go. Okay. So let's see. What did I do first? My first argument was just the loop transfer function. So that's the blue line. And you know that should have this gain crossover frequency of 22.3 and so on. Now, the red line is the loop transfer function where I have the compensator and the plant. The orange or yellow line is just the compensator. So what we have here is, whoops, what did I do there? Let me get rid of that. Didn't want to get rid of that. Figure 2, here we go. Just going to move you out of the way because I'll probably want that later. What we have with the red line is the blue line, which is the plant, added to the yellow line, which is the compensator. And that's why the red line is kind of, you know, deformed and pushed up here. We can see that the phase bubble is exactly, you know, the peak of it is exactly where we wanted it, which is at, oh, maybe here, 22.3 degrees. The problem is that commensurate with this phase bubble is an increase in the magnitude of the Bode plot due to the magnitude increase of the lead compensator. So our gain crossover frequency is no longer at 22.3 degrees, but is now over here at 49, or I say 22.3 degrees, I meant 22.3 radians per second, but it's now at 49 radians per second, and so we are not really utilizing the full impact of our phase bubble. Right, we kind of deteriorated here. Another thing happened on the way to this little situation, and that is that, you know, when we started, we had a gain crossover frequency here and a phase margin of 6 degrees. But because we moved to the right of our gain crossover frequency, we also lost some more phase. And that's a bad thing. So what we're going to do is a couple more iterations on this. We are going to now account for the rise of this magnitude plot and adjust where we put this phase bubble accordingly. Okay, so to do that, we can actually do it from this plot. To do that, we need to use another one of our functions. So if I do a who's here, we have all these great functions. Here's the mag drop function. So I'm going to go mag drop alpha. And for this design, where we're asking for 48.6 degrees of phase, the magnitude is actually going to rise 8.5 roughly dB. So to anticipate that, what we're going to do is find a place on the original loop transfer function's magnitude plot that's 8.5 dB below 0, so negative 8.5. And that is, I don't know, somewhere around there. Let's call it 36.6 radians per second. And that's where we want to place our phase bubble. Okay, so I have to keep track of all this, so we're saying 36.6. So let's see here. I'm going to go omega 1 is equal to 36.6. So that's our new location for our phase bubble. And we're still asking for the same amount of phase, that 48.6 degree, degrees. So now I just have to recalculate t. So I'll just go like this. And instead of omega 0, I'm going to say omega 1. And I have a new t. Now I can make a new d. Just like that. Everything looks right there. We can look at that d if you want. There it is. I don't know if that tells you a whole lot. But let's make yet another new Bode plot. And I'll call this figure 3. And d2. And d2. So there's a bunch of good stuff there. Hit the enter. And we get that. Now, let's see what happened. Again, we have these 3 plots. Here's the original plant. Here is the, the plant with the compensator, so the new loop transfer function. And here's the compensator. So here's their phase bubble. And it should be at the right place. And you can see how we have this nice little deformation of the phase right there. Let's see where our gain crossover frequency is. For the red line, it's right about there. 37.1 radians per second. Let's see if I can get any better. Oh, what did we get? Oh, that's good. 36. Look at that. So if I come down here to the red, and I go to 36. Now you can see it's a little bit difficult to get that, right? Well, we can use some of our fancy functions to help us out with that. Because remember, we have this one function that's called eval angle, eval a. So I'll go eval a, and I have to give it the loop transfer function, which I think is that. And 36 should be what we pulled off of the magnitude plot for the gain crossover frequency. Actually, why don't we check that? I'll go eval m first. So this is going to give us the magnitude of g times d2 at 36 radians per second. And that's pretty close. And you can imagine if I make this so maybe just a little bit less, I get that. If I make it a little bit more, I get this. Well, that's even better, 36.1. That's even better. So I guess we would say that our gain crossover frequency is 36.2. So now we could go eval a, g times d2, at 36.2. And we get negative 127. If you add 180 to that, there's our phase margin, 52.5. It isn't quite what we wanted, right? We wanted 55. And the reason that it's off by a few degrees is because if you go back to figure 3, when our gain crossover frequency moved from here to here, the phase went from here to here. And so we lost just a wee bit of phase. And that's where I said that you could use this factor of 1.1, that if you needed 48 degrees of phase, like I think how we started this design, if I do a who's again and PM0, I think it was, no, PMC1, 48.6, you could ask for, 1.1 of that, another 10% of that. Well, that's kind of crude. I mean, really what that is trying to do is trying to capture the effect of this little phase loss here. We could calculate that more accurately by just going to this original phase crossover frequency, which was, I don't know, 22.3 or something, and then comparing that to the new, or did I say phase crossover? The gain crossover frequency, and this is our phase, and then going to the new gain crossover frequency and picking off the phase and seeing how much error we have in the phase, and then fiddling around with the amount of phase that we ask for so that we get that back. So you could do that quantitatively. I can show you how you can do it just, a little bit rough by just saying that instead of 48.6, we'll say PMC2 is equal to PMC1 times 1.1. So we're going to ask for that much phase. And of course, we have to come up with a new alpha. So I'll do this. And great. So now we have to do our mag drop again. And now we're at negative 9.6, let's say, dB. So we have to start all the way back from the beginning of the design, but I can still do that with figure 3. So I'm going to go to the original plant and go to negative, what did we have here? Let me move this out of the way for a minute. Negative 9.6. Right about, oh, I had it. I had it so sweetly. There. Close enough. So I'm going to say 39.1. We can check it here if we really wanted to. We could go eval M of the original plant. And what did I just come up with here? 39, I was thinking it's 39.1. That's pretty close. We want negative 9.6. That's negative 9.7. We go like that. Yeah, I'm going to just call it 39.1. That's close enough. Okay. So, let's see who our variables are now. I'm going to call that omega M2 and say that that's equal to 39.1. And we have an alpha, I think. And so we could form a T. This is now omega M2, and we have a T. And now I could form a D3. Yeah, I should just leave it like that, huh? Okay, and let's make yet another Bode plot. So I'm going to go figure 4. We have a G, a D, but now I'm going to say D3. And we're going to look at all this stuff. Let's see what we get. So, I mean, we could calculate things by hand here, but let me cheat and make yet another plot. Whoops. And I'm going to go Bode, or not Bode, margin, G times D3. And throw a grid on it. Look at that. We got all kinds of phase margin now, 57.2. So, maybe 1.1 was a little bit aggressive. We could have ratcheted that down a little bit and got just to 55 degrees. But it never hurts to have a little bit more. So there you have it. Again, there's just two little things that you have to worry about. One is how much the magnitude plot is going to rise. So you have to adjust where you put your phase bubble based on that. And then you also really need to think about how much phase you want to ask for, knowing that your phase plot is going to dip down a little bit as the gain crossover frequency rises. But let's do one more thing, since I just have a couple more minutes before I have another engagement. So I'm going to say GCL is equal to feedback. I'm now going to make the closed loop transfer function, and that's going to be G times D3, and I put a 1 there for unity feedback. Boom, I go like that. Now before we look at that, let's go back to our loop transfer function Bode plot from the margin command. And we have a gain crossover frequency of 38.7 radians per second. There it is. Oop, right, well, you can't see it, but it's at 38.7 radians per second right there. Now, the closed loop bandwidth is typically about 1 to 2, somewhere between 38.7 and 2 times 38.7. So somewhere between 38.7 radians per second and, let's say, 77. So I'm going to make yet another figure, make a Bode plot of the closed loop transfer function, and pick off the closed loop bandwidth and see where it's at. Let's put a grid on it. That is a classic closed loop Bode plot. Here, what it's saying is that at low frequency, if I were to put in a sinusoidal input as the reference at a low frequency, let's say 1 radian per second, I would track it in amplitude perfectly. Right? This is 1. 0 dB is 1. So I'm tracking it perfectly. Then I get a little bit of increase as I increase the frequency of the sine wave I'm trying to track. Notice, however, even though the amplitude is tracking perfectly, the phase between my input and output is actually not perfect. If that's a problem, that's a problem. And then at this frequency, we're actually going to have the output be a wee bit higher than the input. Now, as I get higher in frequency, eventually I stop. I don't track the amplitude very well. And in particular, what we use just somewhat out of convention is this we call it the 3 dB down point. So where the magnitude plot is -3 dB, that corresponds to an amplitude attenuation between the output and the input of 1 over the square root of 2, or basically 0.7. So the output is now 70% of the input in terms of amplitude. Check out the phase, though. It is way off, 90 degrees out of phase. I mean, if you were to look at these two signals in Simulink or an oscilloscope or what have you, you would see a vast difference between the input and the output, not only in amplitude, but also in phase. The frequency at which this happens is 62 radians per second. That's the closed loop bandwidth. What it's saying is that up to that point, we can track the signal with some level of fidelity, and after that point, not so much. 62 radians per second. Now remember, I estimated it to be somewhere between 38.7 and 77.4. Perfect, right? Almost right in the middle of those two. If we were to calculate the average of those, not too bad. So the importance of this is significant. I mean, this is significant because what it means is that we can stay in this space, this loop transfer function world, to do not only our phase margin and gain margin analysis and perhaps design, but also to design to hit requirements for closed loop bandwidth. That is a bizarre situation, right? We're actually satisfying a closed loop performance requirement using the loop transfer function Bode plot. Freaky stuff. Okay, so that's it for lead compensation, and I've got some other videos on lag. I might do a quick new one on lag just because of where we are and what I know you folks have seen. Maybe that'll be more relevant. So I'll end it there, and we'll see you folks later. Bye-bye.